All right, hello, welcome back. So, the last concept that we want to discuss in the topic of rectilinear motion of a particle is the concept of acceleration. So, I have this cartoon here that originally the particle was at some position S, it had some instantaneous velocity v, and after some time, the particle goes to a different position and it acquired a different velocity, and the velocity would be v prime. Exactly the same way we defined the average velocity, which was change in position divided by time. Now we can take one more step and define average acceleration, which is change in velocity divided by time. So acceleration, the average value, is change in velocity divided by time. That is v prime minus v divided by time passed. This v is v prime. So imagine again a situation in a car. You are sitting in a car, you are stationary, so your original velocity is 0. And 5 seconds later, you have reached 60 miles an hour. So that is a typical 0 to 60 miles an hour number people usually report. That is the average acceleration. And your acceleration is 60. Let me do it. Why am I talking? So, example here. Example, car where 0 to 60 miles per hour is, I don't know, an average car 5 seconds. So the average acceleration, what is this? Average acceleration is change in velocity. So at a later time, you have 60 miles per hour speed minus the original value, 0. You start from 0, divided by time elapsed, 5. How much is 60 divided by 5? 12? 12 miles. Let me write it. Miles per second squared. Now, why is it... No, what did I write? This is not a good example. What do I do? 12. Yeah, let's leave it as that. 12 mph divided by second. That is a weird unit. But you are acquiring 12 miles per hour every second on average. That is the concept of acceleration. Now, well, this is a messed up unit because it's not usually how we report the acceleration. So unit of acceleration, unit of acceleration is unit of delta v, which has meters per second usually, or similar, divided by unit of delta t, which is second, and that gives us meter per second squared. Or similarly, usually what we report acceleration is in feet per second squared, and so on. So note that unit of acceleration is unit of length divided by a squared unit of time. And yes, okay, this is good. That is average acceleration. Again, staying on this topic, I don't know if you have noticed, but if you look at the speed of a car versus time, so this is velocity, versus time. Often in most cars, most at least gasoline engine cars, you will start acquiring speed fast, but eventually you slow down. So until I don't know, you reach your desired speed. If you look at the acceleration at different time windows, you have different changes in velocities. So your acceleration is actually changing, and it is different from the average acceleration we calculated. Similar to the concept of average versus instantaneous velocity we defined before, here we can also define instantaneous acceleration based on the concept of average acceleration we defined before. Instantaneous acceleration. Whenever we say acceleration, we actually mean instantaneous acceleration. And that is when we take these time windows closer and closer to zero. So looking at smaller and smaller time windows. In this case, average acceleration approaches your instantaneous acceleration, A. So A is in fact limit when delta t goes to zero of average acceleration, which is limit of delta t going to zero of delta v over delta t, which is the definition. Now you see the time derivative of velocity, or in a very short notation, v dot. Yeah, okay. So acceleration is time derivative of velocity So one thing to remember here, remember v was ds over dt, and taking another time derivative of that, so a, that is dv over dt, it becomes d2s dt2. So in other words, acceleration is also equals second time derivative of position. Oh, why is it so thick? So first time derivative of velocity, or second time derivative of position. And yeah, I think that is all I can say. We talked about the unit. We talked about one other thing. And this is short form notation. We show it with two dots. ds, second derivative of time, second time derivative of position. We show it with two dots on s. Yeah, okay. I have a few tiny remarks that I leave it for another video, and that would be it. So I'll see you then.